work as well. Right here. Okay, so we ended with that question 5, what was actually a very nice question about the graphs of my induced EMF and my magnetic flux. That was very nice. I actually went and I got an article that the guys investigated, well, the pendulum motion of induced EMF and the flux, and have the graphs for that with a data logger. And the same as with question 7, when we get to question number 7 as well. I'm going to post that for you guys as well. I'm going to save it for myself for reference as well, because it compares the different graphs that you get for magnetic flux linkage and the induced EMF of that. And as we said, the EMF is actually the gradient of the magnetic flux. So just a bit of a wow info moment on my side in any case. But let's get back to question number 6. And you'll see with 6a, I have not written in anything. They say, explain why the generator is easier to turn when the lamps are switched off. Okay, so this is a AC generator used to provide electricity for a lighting circuit. What do you have?
Well, I have what you have, actually.
You have what I
initially,
have. Yes.
Yeah, initially. Oh, wait. Are you talking 6A or 6B now?
It's 6A, yes, the empty space.
6A, oh, sorry. I said when the lamps are switched on, there would have to be work done to turn on the light energy for the lamps. Whereas when they're off, less work would have to be produced, since none is going to produce that light. But I wasn't really sure about this one. This question was kind of weird for me.
You know what? It is weird in the certain sense that when you have your coil turning between the magnetic fields, or when there is an induced EMF, there's also a circuit within your coil being produced. And,
right.
So not only for your external circuit, and I find it hard to draw that. So it's not only within your coil that you have this current being produced, but also inside that. And they talk about eddy currents. Now, I looked at your syllabus and I couldn't find the word eddy current there, and I'm convinced we had it in a question last year. It might have been an older question paper, because that is the force that they use to for damping. So if you have, and you remember the setup for one of your magnets being attached to a spring, and then it goes in and out of a coil, it bounces, so you can get your oscillation moving up and down there. But the oscillation is damped because of the current being produced in there, in your coil, with your magnet going in and out. So that is one thing. So actually what happens in a question like this, where there is a current being produced, there's actually resistive forces being produced by eddy currents within the coil. And that's what makes it harder to turn when it is when there's a current flowing than when there's no current flowing in your circuit. But the word eddy currents doesn't occur anywhere in your textbook, neither in your syllabus. But I think it's worth it. They could definitely, they should accept it and will accept it. So you can, a good way to state that is when it's when there's current flowing, eddy currents are produced within your coil that produce, or that give resistive forces against the turning of a generator. And those resistive forces will be absent when there's no current in the generator or in the circuit.
All right.
One of my slides refers to that on the electromagnetic induction. I have a slide there that talk about the application of, and I think that's where we had it last year, application of induced EMS. So you can have a look at that. It gives a bit of an indication of what happens and where the eddy currents are produced. But as I said, it doesn't seem to be that essential for the syllabus that you know, that you should just know there are actually other currents, or if there's a current produced, there are resistive forces within the coil also working. Because remember, the whole thing about Lenz's law is also that it wants to prevent that motion in there. You know, conservation energy. You want to not have that. Okay, so that's me trying to explain eddy currents with not having any picture in front of me. Okay, BI and BII. Listen, I looked long and hard for this little equation.
Yeah, initially I also couldn't find it because I kept just doing band times frequency, but then I saw the one where they use W and then.
Yes, where they actually use the angular frequency of it. So
yeah.
And once you know you can use that, then obviously it makes sense. Then BI and BII are sweet and short actually. So this is interesting. So when you have a coil turning and they give you the frequency, you can actually use that in there. I must say, I would still like to go just a little bit deeper and get down to the bottom why they use that, because one of the other equations that they give in the textbook, there is an equation for when you have a disk, and then it's just times the frequency and not times the angular velocity or frequency.
Yeah, that on page 285. I also looked at that one first, but then I thought it had to just be because of the disk, so I can't use it.
Yes. Yes, it's not a disk. So, you know, I even tried thinking about the rotation producing a circular rotation, but I presume that's why they get to this. I'll look at that a bit and get back to you guys on why they do that.
Right.
But you say, after you got this equation, yes, then everything is sorted. Right.
Yeah, then it was
question number 7. And it's question number 7 that got me to that little article that I spoke about when we started, because now you have this bar magnet that's held horizontally in or vertically in a horizontal coil connected to a data recorder, and it shows the diagram below. When the magnet was released, the data recorder shows in the diagram below. When the magnet was released, the data recorder was used to measure the voltage induced in the coil every 5 milliseconds. The diagram shows how the voltage changed with time. Okay, so there's the coil, and then this is the full EMF one. Am I now right? Yes. This is the full EMF. So the part that we're seeing in the book is literally that part.
Yeah.
To close it with actually. So is this where this is my induced EMF when it falls. So it's actually within the ring. It's not falling from above. It's actually just the last part falling out of the ring that it shows. And then your magnetic flux graph looks like this. Magnetic flux looks like
But
this.
is that a straight line, sir, or is it?
No, it's a curve. You know what? After I thought, it's not a straight line. You're going to have something like that. So it's more curved than a straight line in there, because this it's this up and down in there. So they're going to have a slight curve. And I only realized that, as I said, after I drew it. So it's going to look more like that. It's going to be more of a curve. So this is very nice if you have the full picture of what happens, because this is also then, you know, the second part of it, the B part. You know, if we let it fall from the top, goes through it and out the other side, then you have this complete picture of it. So I think, not to say, you know, memorize it, but it's good to put the whole picture in one's memory of how induced EMF time and flux linkage, change in flux linkage to delta T, or flux linkage, not change, flux linkage to time looks like. If you have that, then I think one is sorted. Yeah. Happy with that?
Yeah, makes sense.
Okay, let's look at question number 8. We go over to our transformers.
Wait, so isn't there still a I and a B part to that question?
Oh, okay. So this whole thing, that first part, this actually is your A that you need to draw. B is the whole thing. And then there is a II. It says, use your graph to explain the shape of the voltage V time graph. And what did you get there?
Well, I pretty much said that if you looked at the induced EMF or the voltage, it's the gradient of your flux linkage time graph, because your flux linkage per time is your induced EMF.
That's it.
So you can just look at the gradient of that graph and go from
exactly. So the change in flux linkage, which is your gradient of this, is equal to that.
Yeah.
Interesting enough, they say it's negative, the gradient. So the negative part comes from Lenz's law.
Oh yeah, that has to be in the opposite direction.
Opposes the action, yeah. So just add the negative in there for me. So as I said, from Lenz's law, it comes from that. Right. So very important. I think we'll see these graphs that I can remember quickly from our worksheets, or from our worksheets. We'll see them quite frequently in those two worksheets on magnetic induction. Okay, let's get back to our transformers. Now, did you ever do transformers in ICSI? Do you recall something like that?
I don't think so, actually.
No, I don't think you guys did the full ICSI and got to all of that. No. So very simple is we can work with this ratio of your potential difference over your secondary coil over the potential difference in your primary coil equal to the amount of turns in the secondary coil over the amount of turns in the primary coil. Now, the textbook shows how they get to this ratio, and they call it, I think, the law of transformers or something like that. Let me quickly get to.
Yeah, they do.
Something like that. Now,
they just call it the transformer rule.
Transformer rule. Okay, you don't need to know that how to derive that whole equation. What you need to do is you need to apply. Okay, and it's a ratio. So whether you have Vs over Vp or Vp over Vs, you must just make sure that if it's secondary, secondary is on top, and primary, primary is bottom. It's a ratio. You can just write. So no problem with that. And for our first question, we just substitute. So they have that 230 volt to 12 volt transformer and primary coil with 1,000 turns. Calculate the coils in the secondary one, no worries. And please remember, all of your electricity will be applicable to this. So any equation there is going to be applicable. Very important is though and I'm not going to spend time on this, the BI and II, I presume you got it. So power is
yeah, but I calculated II differently actually. I used that ratio that they give at the bottom of page 9, where they say that the current of the secondary over current of primary is equal to the voltage of primary over voltage of secondary.
Perfect. Because it plays down to the power, né? So
yeah,
same thing. You can use that.
Well, it could have just been way easier if you just did the power like that.
Yeah, you could have done that. It's the same principle. That's good. What is important, as soon as they talk about the heating effect, it's mostly the power due to the resistance of something, conducting wire that is lost. So heating always refers to this ratio. The potential difference doesn't matter, but your current flowing through that resistor of a specific resistance. So I just added that because this is quite important to know. That's the heating due to resistance, and we use this. And it's that power loss thing. So that's the question that they ask is estimate the power wasted or lost due to heating or heating effect in the cable. That's nice. And then they ask, what if instead of using a little bit of a transformer, we plugged it directly into our 230 so we didn't step it down? Well, the heating would be much less. So then what is to discuss whether or not it would be better to replace the lamp and transformer with a 230 volt 60 watt lamp to the mains using the same cable. So
I just said yes, it would be, because the heating effect would be less, or less power is dissipated.
One thing that you need to be careful of, and the memo mentions that, is that, you know, that cable could be only for a 12 volt potential difference. So it could be a safety hazard. You now put 230 volts through it. So that could be. So, you know, depending on the marks allocated to a question like this, if it's 1 mark, this answer would be sufficient. If it's a 2nd mark in there, I would add that safety margin or safety feature in there. Say, you know, a cable could only be suited for a 12 volt potential difference and not a 230 volt.
Yeah.
All right. So just in that sense. Let's look at, listen, question 9, I just said theory. Wow.
I'm not gonna lie, I initially skipped it and then I never came back to this one.
Yeah, no. Listen,
I just forgot about it.
I think this might be something that you rather get in a question paper 5, where they will more or less guide you in telling you, you know, this is the type of relationship that you get between a bar magnet and an ammeter or magnetic flux, and give an outline of the experiment. I don't know whether they'll put Lenz's law in there, but the only thing that you need to do is you need your coil and you need your connecting wires from your coil to a sensitive ammeter, and then you need to put your bar magnet in for the North Pole, and you need to explain what happens. You know? And it's the same as this question. Let me go back to our question that we had last time. If you can just talk about this. So if you push bar magnet in with a north, there should be a north being produced because it will oppose it. How would we find that out? Well, if there's a north there, my current will flow, and you talk about how your needle would, and which direction your current would tend to flow. And then the opposite as well. And that would be providing evidence to support Lenz's law. And that's it. So it's a lot of scribble, but if you have these two pictures, then I think you'll remember what to do. For me, the last question was quite interesting, and I'm still stuck actually at the last bit, and perhaps you spend some time on it and you can actually assist me with that. There we go. Let's just get back to it. Okay, so as I said, this is also a 2010 paper coming from a question like that, and they give you the circuit and ask you to fill in the diode in your rectifying bridge. Okay, so we talked about this last time, and yes, we need the 4 diodes, and it must be in such a way that when my current goes into this side, it must only go in one direction. So in the can't go in there, must go in that direction. And we're talking about conventional current, and that is always the positive side. So it must produce a positive. So going in, can't go through there, must go there. Right? So very important to get the direction of that. If I'm done with this, the flow of it, it's going to go back in a different route or going through there. This is probably going to be the better route for it to go through because that is more resistance. Remember, one's current always chooses the path of least resistance to move through. So you'll probably have this route going through there and thereby producing a direct current with this whole system. Right. Okay. So, and it's 2 marks to put in the 4 diodes, which is really for free, actually.
Easy peasy.
A different way of looking at this is also, I'm saying rectifying bridge, but if I'm recording correct, it's a Wheatstone bridge connection as well. They refer to that. But I'm not 100% sure if that's diodes or resistors. But no matter, that's the way it looks like. Right. Then they ask, calculate the ratio of number of turns on the secondary coil to number of turns in the primary coil. And just face value, this is okay because they give us the voltage, direct voltage of peak value 9 volt is obtained from a 240 volt alternating supply. So, and remember the ratio we said we can get from this. So if we want the ratio of secondary coils over primary coils, we can get it from the potential difference secondary over potential difference primary coil. What bothered me in here is that this is then your RMS, the RMS according to the way I calculated it, and this is your peak voltage. So 9/339. This gives you the ratio answer in the memo.
Yeah, I did it the other way around, where I looked at that the 9 volts was my, because it states that it's the peak value. So that if you look at page 288, they give that formula there where you do 1/√2 times the peak value.
That's it, yeah.
So then you multiply that by the 9 and then divide it by 240. But I guess that might not be correct in the sense that the 240 volt is the alternating supply.
Yes, and your direct current is just this steady one. That's not the one that goes up and down. So it is your alternating one that you need to work with. But this is weird for me in the sense, in question number 8, they also just talked about the alternating voltage of 230 volt and 212 volt. So they give that and they don't refer to it as peak or as RMS. Neither in here they actually refer to that. They just said that the direct voltage of peak that is 9 volts. And this threw me off a bit. The wording is definitely something that one needs to just be really aware of when you look at a question like this.
Yeah.
Right. But I think we'll find many more questions like that in our worksheet, as I said. I just need to finalize the 2 worksheets and then post it for you at the stage and for Ruben. And
Right.
it is, let me just quickly look. I've got the hard copies here. I haven't manipulated it as I would like to at this stage. 1, 2, 3, 4, 5, 6, 7. Okay, my worksheet 2 is quite a bit longer than my worksheet 1. I'm going to manipulate that so that I can break it up into 2 more manageable parts perhaps for you guys.
All right.
For the next time. If I look at this, my worksheet 1 is actually a more important one, while my worksheet 2 is actually getting to my bit where we have the damping effect of a coil. Okay, but don't worry, I'm going to do these for you and then post it, let's say, before 2 today on Moodle.
All right.
And you guys can start. Any questions from at this stage?
No, that's all fine now, I guess. It was only actually that 6A, which I found really confusing.
It was, you know what, because there's no real information except if you go and dig a bit deeper. And if I didn't know about the eddy currents, I would also not have mentioned anything about that. So yeah, have a look at that and then post this. And then listen, can we then how is your week looking? Are you quite good with tests, or how's the maths going?
Well, the maths, we actually don't have a test yet. That's scheduled for when we, after the midterm break when we get back. So we just have work to do. Same as the stats right now. We also, because stats, we just started a new chapter, and geography, we pretty much finished all of our hard work that we were doing last week for Cambridge. So
okay. Yeah.
Everything's a bit more relaxed right now this week.
Okay. Listen, then I would ask that we, Wednesday morning, perhaps, if you guys are finished with the worksheet, or at least some of the first questions, that we'll work through that so that there's less for Friday. And we can work through
Right,
this.
makes sense.
Yeah. So Wednesday at 8, but I'll keep me up to date. I'll ask on Tuesday afternoon again how far you guys have progressed with the worksheet. Otherwise, we just do Friday. You know, I also don't want to push too hard. Pushing hard and not too hard is a very fine line. We're well on our way to finish. It would be nice if we can finish magnetic induction this week. If not, then that first Monday after the midterm break, we finish that, and that Friday we write a test on magnetic fields and magnetic induction. That would be the aim.
Right.
Right. Okay, but I'll post it, and then I'll ask tomorrow both you and Ruben and see where we are. Okay.
Right. Thank you so much.
Right.